Hello,
Hello, good evening.
good evening, ma'am. Just give me a couple of minutes. I'll just set up my tab and
Yeah, if you have time, then can you discuss Earth-first equation or Earth-first theorem? And secondly, Landau levels. Professor Ramadevi, she discussed about this when some degenerate levels in the presence of a magnetic field, and the amount of degeneracy depends upon the magnitude of the magnetic field.
Okay.
So, yeah.
Yeah,
Actually,
yeah.
my background is not from physics. I am basically an electronics person.
Yes, yes.
Whenever there's a reference of something that refer to the classical mechanics and things like that, na,
Okay.
then that becomes difficult for me. Yes.
So, okay. So, how about, because these two things are little, what you say, separate from each other.
Yeah, they are separated.
Yeah, so what do you want to discuss today? So what we can
On
do is we can discuss one of the things today, and
yeah, okay, okay.
second one maybe in the
Whichever,
next session.
yeah, whichever you feel.
I think Aaron Fest should be discussed first because
Yeah,
it relates this classical to quantum,
right. Yeah,
and then after that maybe
sometime,
yeah,
Landau level.
sometimes we can discuss Landau levels.
Yeah, and one more thing. What
Yes,
is Lagrangian?
Lagrangian.
It took me some time to understand what is Hamiltonian. To be very frank, because
Okay.
my background in quantum is I'm building it up. Okay, so now I understand what is Hamiltonian,
Mm-hmm.
but what is Lagrangian? So that also is sometime you get time, so just
Okay,
yeah.
then I think we should first start with Lagrangian itself
Okay,
before going into anything else. Yeah.
okay.
Okay. So, I mean, Lagrangian within itself will take a one complete course of classical mechanics,
Okay.
but I'll try to give you a very quick idea. In the
Yeah.
meanwhile, if somebody wants to join, so let's
Yes.
have a quick 5 minute discussion.
Yes. Yeah.
Yeah. Okay. So, okay, Lagrangian. Let's do it. So it is defined as, write its definition. So this is its definition. Basically T minus V.
Okay, so
Okay.
this is very simple. Hamiltonian only then. No, Hamiltonian is plus T
Yeah.
plus C.
Okay, I'll write Hamiltonian, which is T plus V.
Okay.
So Lagrangian is the difference between our kinetic energy and potential energy, whereas Hamiltonian is more like total energy because we are adding the two. In Lagrangian, we subtract the two. So, like when we study classical mechanics, there are actually two paths. One is called this Newtonian path, right? The Newtonian mechanics, which is mostly based on our force, right? The second law of Newton, which is,
F is equal to M.
yeah, F is equals to ma, or
Mm.
this dp dt. Yeah.
Okay. Okay.
And notice that this is a vector equation,
Mm.
whereas this Lagrangian is a scalar because it has energy and no direction. So for Newtonian, this approach, the question that we ask is that what are the forces acting on our system, and once we know the forces that are acting on our system, also the initial conditions, let's say x naught v naught, right? Then
Mm-hmm.
in principle we can explain the uh, entire path that the particle will take.
Okay.
So we need to know all the forces that are acting as a function of time, the initial position, initial velocity, these things. But in this Lagrangian, instead of force, we say, okay, if this is my Lagrangian, also this Lagrangian will be just like how this force is a function of t, right? My Lagrangian is also a function of t because my energy is changing with time. So, the reasoning is just like in Newtonian mechanics. If we know how our force is changing, then we can use that to tell how our position and velocity of the particle will change in time. Drawing that analogy here, if we know how our Lagrangian is changing with time, we can determine how our position and velocity will change in time. Okay, so how do you do that? So here, like, we know that this is called equation of motion, right? This is equation of motion. If we define Lagrangian for a system, how do we get the equation of motion from a Lagrangian? So that is called Euler-Lagrange equation. Euler-Lagrange equation. And if I remember correctly, I think this is partial derivative. So this is the equation. Note that this q dot, so q is our position coordinate, let's say x, and q dot then will be our velocity coordinate, let's say dx by dt. Okay, so this is qi is position and qi dot is velocity. Okay. So basically then our goal is that we write the Lagrangian using this first equation, t minus v, for any system, put this Lagrangian into this equation of motion, and what we will get is the equation of motion. So what I can quickly find a example. Okay. So okay, let's look at a simple pendulum. Yeah. So we have a mass m, right? And let's say this is our string, this is length L, and this is some angle theta. Okay.
Yeah.
So now what will happen? We can write our height as h will be, so this is L and this will be h, right? This will be h. So h will be L 1 minus cos theta, right? So that when theta is 0, no.
Yes, I
It will be L cos theta. Just L cos theta. Yeah?
Okay. Now yes, it's
No, sorry. Yeah, I confused. So height will be, so this is, let's say, our equilibrium. So this will be our height, h. Because this is the, here we are defining our potential to be 0. Right? Here potential is 0. So the height will be this much. And this height will be L, and now 1 minus cos theta. Yeah? Because this up to here, this will be L cos theta, and we have to subtract it from L, so L 1 minus cos theta. Similarly, our velocity v will be nothing but L theta prime. So theta prime meaning omega. Yeah? So our velocity is simply omega L. Okay? Now we can write our kinetic energy as half mv square, or putting v, we will get half m L square theta dot square, and our potential energy mgh will be mg L 1 minus cos theta. Okay. So continuing, our L will be t minus v, or mgl, t minus v. So half m L square theta dot square minus mgl 1 minus cos theta. Now using this equation, the Euler-Lagrange equation, we can find out these partial derivatives. So here our q is theta, right? Instead of q, we will have theta. Okay? Okay. So our del L by del theta dot, this will be simply ml square theta dot. Yeah, so this half and 2 will cancel, and del L by this thing del theta, this will be simply this second term, so minus mgl sine theta. Correct? Now we will just plug them here. So if we take d by dt of this first term, d by dt, so what will we get? So ml square will remain constant, and instead we will get theta double dot. Yeah?
Okay.
And then this is as it is. And if we take the difference, that should come out to 0. So basically what we will get is, we will get ml square theta double dot plus mgl sine theta is 0. Right? So this m will cancel, and we can write this as theta double dot is equals to minus g by L sine theta. Right? Which is the equation for a simple pendulum. Okay, notice that here we didn't need to resolve the force in any direction x or y and then apply the gravity downwards or anything. There is no vectors involved. Yeah, there is no vectors involved. It's just, everything is just energy, and from energy what we are getting an equation in theta, right? And the equation is telling us how this theta is changing with time. Yeah.
Yeah.
And then if we take our approximation that this theta is very small, so for a very small oscillations, then we can write sine theta as theta, and then this becomes simple harmonic motion, right?
Yeah.
Because our acceleration is proportional to like theta double dot proportional to minus theta, right? So acceleration proportional to minus x, let's say, and our under root g by L will be the omega, or the angular frequency, right? So this is one way of doing classical mechanics. Okay. The other way which we are generally taught in schools is the Newtonian mechanics, because that is, I would say, more intuitive. Yeah, because
Yeah.
you can think in terms of force. Here we didn't think in terms of force, we just thought in terms of this L minus V, and this is generally very difficult to explain why some quantity which is the difference in the two energies will give us the equation of motion. Yeah, this is not very intuitive thing to understand. Like if we take the difference between two energies, why should we then get equation of motion? However,
Yeah.
when we think in terms of force, I think it is much more easier to explain things and also easier to grasp that we are pushing something or pulling something, so it should gain some momentum or it should lose some momentum, its position should change accordingly. But in terms of energy, it is little non-trivial. But it however, like despite this, the advantage is here we just forget about this vectors. So when we are in, let's say, n dimensions, not just 3 but we can have n dimensions, so there this, when writing the Newton's equations, like then we will have n equations, right? Because if you notice, like these are 3 equations, one for x, one for y, one for z. Yeah. But if we have a many body system, for a many body system we then have 3 n dimensions, 3 dimensions for each, and then the sets of equation is just increasing like tremendously. Instead, if we just consider the energy of the system, the total kinetic energy and potential energy, then things become, I would say, little easy. Yeah. So that is why this that is the advantage of this Lagrangian way of doing things. Okay.
We can now start with the
Yeah, I
your
think we have already spent quite some time. So we'll discuss this Ehrenfest's theorem in the next one,
yeah,
and the Landau levels in the
maybe
maybe in
next
the
one.
next to
Yes,
next.
yeah.
Yeah. Okay. So today it's just you. Okay. Doesn't matter. I'll upload this on YouTube and people can watch it there. Okay, so let's start. So this is the first question that we are doing, and it it talks about the triangle inequality. So what is the triangle inequality? The triangle inequality. This we also study in linear algebra, for example,
Mm.
where we say that this quantity mod of a plus b, this is less than equals to mod of a plus mod of b,
Good.
right?
Okay.
This is the triangle inequality. It can be numbers, it can be vectors, this comes everywhere. So this is equal when these two vectors are parallel, then this will be equal.
Mm.
But if they are not equal, then this will be always less than this. Okay. So here we have psi and chi. Okay, and these are like a and b, and we have to show that they also satisfy the triangle inequality. So if they show, the statement is true. If they don't, then the statement is false. Okay, so first thing that we should notice is that phi 1 and phi 2, which is the basis vectors, phi 1 and phi 2 are orthonormal. So when we take this thing or this thing, this will be 1, but this will be 0. Yeah, because they are orthonormal. Now let's find out this norm, right? So this is norm, which we generally write as mod. Yeah. So for psi, this is psi. So its norm will be, so here it is 3i. So 3i squared, and then here it is minus 7i. So minus 7i squared. Okay. So mod of 3i is simply 3, 3 squared is 9, and mod of minus 7i is 7, and 7 squared is 49, so this is 58. Right? Similarly, mod of chi, okay, so here it is minus 1, minus 1 squared, and then 2i iota squared. So this will be just 1 plus 4, which is 5. Okay, squared. So now we have these things. So our mod psi plus mod chi, this thing will be under root of 58 plus under root 5. Okay. So this is our right hand side. Okay, this part, RHS. Yeah. Let's do LHS now. So for LHS we have to first add these two. We have to add psi and chi. So these are like the basis vectors. So this will be 3 iota minus 1. Yeah. So adding them will give us, it will give us 3 iota minus 1 times phi 1, and then minus 7 iota plus 2 iota times phi 2. Okay, and now we have to take the mod square of this quantity. So psi plus chi squared, again this will be mod 3i minus 1 squared. Okay, so this will be 3 iota minus 1 squared, and then so this is 5 iota, yeah, minus 5 iota mod squared. Okay, so mod of 3 iota minus 1, this will be, this we can write as 3 squared minus plus 1 squared, and then plus 25. So this will be simply 9, 10, 25, 35. Okay, so basically taking the square root, we will get psi plus chi. This thing will be under root 35. So this is our LHS. Yeah, and then we can straight away see that our LHS is less than RHS, because under root 58 is already bigger than under root 35. Okay, so this will be this statement is then true. Okay, any doubts? Okay, so let's do the second problem. Consider two operators A and B which are Hermitian and they commute. Then the operator, which is written as some combination of A and B, is unitary. Okay, so we already have dealt with some unitary operators. If you remember, an operator is unitary if, okay, let's say an operator, let's give it some name, U. Okay. An operator is unitary if U dagger U is our identity matrix. Okay, so this is identity. Okay, and the question asks us to check if the operator that they have given, which is written in terms of two Hermitian operators, if that is unitary or not. So here our U is, let's write our U as A plus IB divided by under root A square plus B square. Okay, note that A and B are Hermitian. Okay, I'll just write here, and P dagger B, because they are Hermitian. Now to check if this is true, the first thing that we need to do is we have to take the adjoint, which is U dagger. So U dagger will be the dagger of this entire thing, right? So what we will get, so this a will remain a, but this plus iota will become minus iota because we have to take the conjugate, right? And then this thing will remain same. Okay, and because these are Hermitian, so we can again convert it back to a and b. Okay, just like that. Now we have to multiply these two, so we have to do u dagger u. So if we multiply u dagger u,
One
yes,
is A Hermitian, then A square is also Hermitian.
yes,
Okay.
okay. I mean, we can do a quick proof if you want. So let's say we have this thing and we take the dagger of this. So this will be simply a times a dagger. So a dagger, a dagger. So a or a square. Yeah. Okay. Moving on. So u dagger u multiplying, so these two, this one and this one, our denominator remains same, right? So this square roots will go away. So essentially what we'll have a minus ib, and here we'll have a plus ib. Okay, and then this a square plus b square and one more a square plus b square. Okay, so let's expand the numerator. Okay, and just writing the numerator now. So our numerator, let me write numerator. So this will be, if we multiply, this will be a square, yeah, and then plus iota ab, which will come because of these two terms, the first and the last one, and then this second term will give us a minus sign, so minus iota ba, right, and then b square, b square. Okay, now one more thing that we should keep in mind is this very important information given in the question, that a and b commute with each other. Okay, till now we have made use of their hermiticity, but they also happen to commute with each other. So because they commute, so this becomes a squared, let's take iota outside, this becomes ab minus ba and b squared. So we can write this as the commutator of a and b, right, a comma b and b squared, and we know that they commute with each other. So this term goes to 0. What we are left with ultimately is a squared plus b squared. Okay, so our numerator of this thing is simply a squared plus b squared. So coming back, we can write u dagger u as a squared plus b squared. Also note that denominator is a squared plus b squared. These two square roots will just give a square, so we'll have a square plus b square. And what this gives us is the identity matrix, yeah, identity. because this condition is satisfied, so we can call that this is a unitary operator. So the answer will be true. Okay? Is this clear? Yeah. Okay. So we made use of the hermeticity, and we also made use of the this condition. Which condition? This commutation, that both of them commute. Okay. So let's go to the next one. So here we have a one-dimensional particle. Okay. So we have already solved some similar wave functions. Can you tell me what this wave function reminds you of?
Is it particle in a box?
Yes. So this first term, which is the sine pi x by a, this comes because of particle in a box, yeah, and like the infinite potentials, right? And they have mentioned that this is confined within the region 0 to a. Okay.
Yeah.
And this, you see the second term, this is just a phase, right? It's exponential iota omega t. So this is just a phase which is telling us how our wave function is evolving in time, right? For example, at time t is equals to 0, the phase is 0, and then this phase is oscillating in time. So this wave function is having oscillatory behavior in time while having a sinusoidal behavior in x. Okay. So okay, so what does the question ask us? The question asks us to find out the probability, okay, probability of finding the particle in the interval a by 4 and 3a by 4. So if this is our x-axis, let's say this is our origin at 0 and this is a, so this will be a by 4 and this will be 3a by 4. Okay, so we are interested in this region basically, and we have to find the probability that the particle is in this region at the time we are measuring. Yeah. So okay, so one thing is we know that this is a sine function. Okay, we know that this is a sine function. So it will be 0 here, right? It will be 0 here and 0 here. Okay. So basically this information already tells us that the probability will be greater than half, because probability in these regions, right, because the wave function must go to 0, so this should be already already enough for us to say that the probability will be greater than half. So let's find out what the probability is. Now if we look at our wave function, the first thing that we can notice immediately is that the wave function is not normalized. We know that the wave function for a particle in a box has a under root 2 by L kind of a normalization constant. So let's first normalize this thing. Okay, so for normalization, okay, first let us write our wave function psi as some, let's psi xt. Let's multiply a factor here a, and then write sine pi x by a exponential minus iota omega t. Okay, and now let's find out what this a is. It should come out to be under root 2 by a from our prior knowledge, but we can do a simple integration from 0 to a squared sine squared pi x by a, pi x by a dx. Note that this exponential term, because it has iota, so minus iota plus iota, they'll just cancel out each other when we do psi star psi. Yeah, when we do psi star psi, this exponential term, they'll just cancel out each other. So we are left only with the x component and square of that thing. So we know that this should come out to be 1. Okay, and if we perform this integration, because we already know, this gives us under root 2 by a. Okay, okay. Therefore, we have our psi as, this is our normalized, so psi norm, normalized psi under root 2 by a sine pi x over a, and then exponential minus iota omega t. Normalization is very important when we are talking about probability. Otherwise, we will just get some random number which will not necessarily be between 0 and 1. So normalization will ensure that the probability that we are getting is always less than equals to 1. It will never be more than 1. Okay, if we don't normalize, then God knows what we might get. We might get probability as 100, which will be completely unphysical. Okay, so normalization is very important first step that we should keep in mind. Now to find the probability, we already have our wave function, and now this time we only have to change the limits. So instead of 0 to a, we are interested in the region a by 4, so this region a by 4 and 3a by 4. So upon squaring, so this will be just 2 by a sine squared pi x over a, and again this exponential terms will cancel out each other when we do psi star psi and dx. Okay, now how do we integrate this thing? If you remember, so what we do is we take out this, okay, let me quickly write this as, let me take out 2 by a outside, a by 4, 3a by 4. So to integrate sine square, what we do is we write it in terms of cos function. So cos 2 pi x by a. So basically sine theta goes to cos 2 theta. Okay, and this complete thing divided by 2 dx. Okay, why? Because we know sine squared theta is 1 minus cos 2 theta by 2. Okay, so now these 2's will cancel out and we'll be left with 1 by a. Now this first term integration will just give us x, and the second, so this will give us a factor of a over 2 pi, and then 2 pi x over, sorry, I missed out. So integration of cos will give us sine 2 pi x by a from a by 4 to 3a by 4. Okay, so let's take the limits. So this will be just 1 by a, so this x will give us 3a by 4. Okay, and at 3a by 4, so this a will cancel, so this will be sine of 3 pi by 2. What is sine of 3 pi by 2? 3 pi by 2 is minus 1. Yeah, minus 1. Yeah, okay, good. So this minus minus will become plus, so this will be plus a by 2 pi. So this is when we put x as 3a by 4. Now we'll put x as a by 4. So this will be a by 4, and now this time it will be pi by 2, so plus 1. So this remains minus 2 pi. Okay, I hope I have done it correctly. Please do cross check once. Anyway, so this is just 1 by a, and this 3a by 4 minus a by 4 will give us 2a by 4, which is just a by 2. Yeah, and this a by 2 pi plus a by 2 pi will just give us a upon pi. So these a's will cancel out and we'll get 1 by 2 plus 1 over pi. So as I said in the beginning, you can notice that this probability p is already greater than 0.5. So I think we are doing it correct only. So p is then 0.5. Let me quickly calculate the value of 1 over pi. 7 by 100. Okay, so this is roughly 0.32. Okay, so finally what we get is 0.82. Okay, so this is the probability that we are getting. Yeah, so pretty straightforward problem. Just normalize the wave function and then take the integral from a by 4 to 3a by 4. That's it. Okay, I hope this is clear. You can ask if you have any doubts, or else we'll go to the next problem, which will be, I think, problem number 4. Okay. Okay, so we have a system which is initially in the state psi naught. Okay, and notice that it is written in terms of phi 1, phi 2, phi 3, phi 4, which are the eigenstates of the system's Hamiltonian. Okay, so these are Hamiltonian eigenstates, and this is the equation that they satisfy. So let us quickly write down this equation. H of phi n will give us n squared epsilon naught phi n. Okay, it is given that this epsilon naught, this is the ground state energy. Okay, what is the initial state of the system? So it is psi naught. It is given in terms of these phi's. So under root phi 1 plus under root 3 phi 2 plus phi 3 plus phi 4. Okay, notice that this is actually normalized. So this 2 square, so this, okay, so root, so this will give us 2, this will give us 3, 5, and then 1 squared is 1, and this 1 squared is 1, 7. So we have already divided by 1 by root 7. So this psi naught is normalized. Okay, now we have the Schrodinger's equation, this Hamiltonian equation, and we also have the initial state of the system. Now the question is, if energy E2 is measured, its value and the probability will be respectively, and then we have 4 options. Okay, so let's first find out the value of E2. So from this equation, we know that the energy goes as n squared. Yeah, so we can write our En as n squared epsilon naught. Okay, so simply E2 will be just 2 squared, which is 4 epsilon naught. Okay, so it's either option A or option B. Now we have to find the probability. Okay, so the probability of measuring this eigenvalue is the absolute square of the coefficient with the state in the normalized wave function. Okay, so this basically this E2 corresponds to phi 2. Okay, this thing here, this one. Yeah, because if we put phi 2 here, So we'll get 4 square epsilon naught, right? So essentially, when the question says that what is the probability of measuring E2, that is same as asking what is the probability that our wave function psi naught will collapse to phi 2. Okay. So what we have to do is we have to find out, so the probability P will be phi 2 psi. Correct. Now notice that if we do this procedure, so these cross terms like phi 2 phi 1, phi 2 phi 3 or phi 2 phi 4, they'll give us 0, and this phi 2 squared, this will give us 1. So then what we are left with, so then what will be left with is the square of under root 3 by 7. Okay, because this is the coefficient, right? So if we write the coefficient, so this is, so our C2, so our C2 here, which is the coefficient of phi 2, it is under root 3 by 7, and then the probability will be mod C2 squared. So this thing, so our probability is just 3 by 7. So option A. Yeah, any doubts? No. Similarly, what will be the probability for phi 1? It will be simply 2 by 7, right? So this 2 by 7, here you have 2, here it is 7, so 2 by 7. For phi 3 it will be 1 by 7, and for phi 4 it is again 1 by 7. And if we add all these, we'll get the total probability as 1. So that is also one way to check if we are correct or not. Okay. So moving on. You know what time it is? Okay. Let's do one more, then we can take a small break. So the next problem is that we are given one equation. Okay, we are given an equation that L comma M, LZ comma A and then again L comma M. This is iota H cut for any A. So any A. And then we are asked to find the expectation value. So the expectation value of Z Py. Okay. So first of all, what is LZ? So this is the angular momentum operator, and it is given by x py minus y px. Okay. Okay. And then we also have these commutation relations. I think these will be taught in the later classes, that our LZ, when it commutes with x, so we get iota h cut y, and similarly if it commutes with y, we get minus iota h cut x. Similarly for the momentum part, we have LZ px, right? This gives this gives us iota h cut py, and Lz py will give us minus iota h cut px. Okay, so these are the commutations. Okay, so let's assume, let so here we are given for any observable a, right, for any a. So let's assume that our a is z px. Okay, let this be our a, and then we have to find out this commutator. So this commutator Lz comma a, what will it give? So it will give z outside Lz comma px, and then Lz comma z and px. Because this z and Lz, they will commute, so this gives us 0. So essentially we are only left with these things, and Lz px we know is simply iota h cut py. So this quantity becomes iota h cut py, right? So then we can substitute this in the equation which is given above. So we are given L comma m, and this becomes sorry, there is also one z here, so z py, z py. Okay, so this becomes iota h cut z py and L comma m, and this is equals to iota h cut. So these iota h cuts will cancel out, and this becomes z py L comma m is equals to 1. Okay, and what is this? This is nothing but the expectation value of z py, right? So the expectation value of z py is simply 1. So the answer will be B. Okay, so basically if you see here, okay, if you look at these equations, right, if you know that whenever we have our angular momentum operator Lz, and then we want to commute it with any a, okay, so we know that we'll have this iota h cut term, right? This iota h cut term will always come. Okay, so this iota h cut and iota h cut will cancel out, and we only have to see if there is some minus sign which is coming along or not. If there is no minus sign, then the answer will be 1. If there is some minus sign, then the answer will be minus 1. Okay, any doubts in this? Okay, so we are halfway through, so let's take a small break and then we'll continue. Meanwhile, if you want to give a try to the next problem, feel free to do so. Let's take a quick 1 minute break. Okay, so let's continue. So here what we are given, we are given one dimensional motion for a free particle and three operators. Okay, so we are given a free particle. The operators that are given to us are Hamiltonian H, momentum P, and parity capital P. And then we have to tell that which of them will commute. Okay, so first of all we have H and P squared. So okay, let's also write the Hamiltonian for a free particle, which is just P squared over 2m, because V is 0. V is 0, so this is the Hamiltonian. Okay, so will it commute? Yes, no? Yes. This is very straightforward, because we can write this Hamiltonian or this P square, we can write this as 2m H. Okay, and of course H and H will commute with each other. Yeah, so A is commuting. What about H and parity? Okay, so we have H and parity. Okay, okay. What about H and parity? Will they commute? Yes, no? No. Okay, so in last session also we had a discussion about this parity. So what parity does? So when we have a this parity operator, so basically it changes from x to minus x, if you remember. Yeah, so that is what this parity operator does. Now if we look at our Hamiltonian, is it symmetric about origin? So as to say, whatever we have at, let's say, x is equals to 5, will we have the same thing? Yeah, it is symmetric, correct. So will we have the same thing at x equal to minus 5? Yes, because our potential is 0 everywhere. There is no x dependence in the potential, right? So we have a symmetric potential. Yeah, since we have a symmetric potential, if we apply the parity operator, okay, let's say this is our just x direction. Yeah, this is our x direction. Because our Hamiltonian is such that whatever happens here is equally likely to happen here, right? There is no difference between these 2 points. So going from x to minus x is not changing anything, right? So this should commute. Is that explanation clear?
So we are seeing basically the effect of parity on Hamiltonian.
Yes, yes, because we want to see if they commute or not.
If had it been the commutation of x comma parity, then it would have been.
Yes, x comma parity, that will not commute. Okay, this will
Uh,
not commute.
but the parity will make x to minus x.
Yeah, x to minus x, correct.
That's why they will not come.
Yes. Okay, so what about p, this parity and p squared? Okay, so next we have parity and p squared. What do you think? Will it commute or not?
Yes, I think it should commute because
Yes, it will commute, because p square is same as Hamiltonian, right? We already discussed. We can write p squared as Hamiltonian. Also, this p square is same, right? It is not a function of x, so as to say, if whatever p square we have at plus x, we'll have the same as minus x. So doing this transformation is not affecting our p square. So this will also commute. So b commutes and c commutes. What about d?
It should not commute.
Yeah, it should not commute, exactly, because our operator p, if you write it in this form, then if we do the transformation x to minus x, we will have an additional sign, right? So this will not commute. In fact, this will anti-commute, right? So this will be an anti-commutator, just like this x is an anti-commutator. I should write this as parity. Okay, so this d is wrong. Only a, b and c, they commute with each other. Okay, if we had, let's say, some potential which was, let's say, some anharmonic potential, some random v as, let's say, some a x squared plus bx. If we had such potential, then things will be different. Now, if we change x to minus x, our Hamiltonian is no longer same, right? So our Hamiltonian will no longer commute. Yeah, but p square will commute, Hamiltonian will not commute. Okay, and then p to already is not commuting. It is just because we had a symmetric potential. For example, this is also a symmetric potential, just the quadratic potential is also symmetric. Whenever we have this symmetry, then our parity commutes with the Hamiltonian. So a symmetric potential will ensure commutation of Hamiltonian and parity. Okay, so moving on. We have harmonic oscillator potential. We were just talking about harmonic oscillator potential, and here it is. And the particle is initially in this wave function psi x0, which is written in terms of psi 0 and psi 1. Okay, a is the normalization constant, psi 0 and psi 1 represent the ground state and the first excited states of the harmonic oscillator respectively, and are orthogonal. Okay, they have written mod psi square as 1 over a something something, and we have to find the value of a, b, c and d. Okay, so firstly let's write our psi x at time 0. I'll drop the time notation, so just write psi x. It is a times 3 psi naught x plus 4 psi 1 x. Yeah, so straight away we can notice that this is not normalized. Okay, so let's first normalize this. So how to normalize? So we have to take this mod 3a squared plus mod 4a squared and equate this to 1. This is the normalization. Yeah, so this is 9a squared and 16a squared, so 25a squared is 1. So a is 1 by 5. So let's write our psi as, so our psi x is then 3 by 5 psi naught plus 4 by 5 psi 1. Okay, now this is normalized. Okay, notice that the question is asking about psi x at some time t, whereas we are given the initial wave function at t equal to 0. Therefore, there is some uh, there is some factor of time in the answer as well. So, we have to consider the time evolution. How do we bring into account the time evolution? We add a phase, if you remember from our earlier sessions. So we add a phase which is e to the power minus I E n t by h cut. Remember? So this is the phase that we need to add. Now here En is the energy of the nth state. So for example, here En will be the ground state energy, and in the second term this will be the first excited state energy. So our psi x comma t will become 3 by 5 psi naught, and then multiply this with e to the power minus. Okay, so what is the ground state energy of harmonic oscillator?
1 by 2 h omega
Yes,
h bar.
1 by 2 h bar omega. So this h bar and h bar will cancel out. What will be left with is omega t by 2. Okay. And then second term psi 1 x. What is the then the first excited state? So this was half, and this will be 3 by 2. We add one more h cut omega. So minus iota and 3 omega t by 2. Okay, this is our psi xt that they mention here in the problem. Yeah, now we have to do what we have to do. We have to take its mod and then square it. So how do we take mod of a wave function? This quantity mod psi x comma t squared is nothing but this thing. Yeah, so this psi star will just give us the complex conjugates. Okay, okay, so let's do that. Okay, before that, what I just noticed one thing. So one thing that we can do is we can take this exponential minus iota omega t by 2 outside, and then we'll be left with this thing. Yes. So now what this will help us with is that when we take this psi star, so this will become e to the plus iota omega t, and essentially e to the power minus iota omega t by 2 and e to the power plus iota omega t by 2, they'll just give us 1. So we have already simplified things a little bit. So then what we'll get is, we'll get the mod of this first term psi star. So psi 0 will remain psi 0, and 4 by 5 psi 1. Now this minus sign will become plus. Okay, and then this same thing again, 3 by 5 psi naught plus 4 by 5 psi 1, but with a minus sign here. Great. So now let's multiply these terms. So this will give us 3 by 5 psi naught squared, and this square of 3 by 5, which is 9 by 25 psi naught squared, right? Similarly, the last two terms, so this last term of the first bracket and last term of the second bracket, they'll just give us 16 by 5 psi 1 squared, right? And then these cross terms, what they will give us, so this 4 times 3 is 12 over 25, sorry, 12 over 25 psi naught psi 1, and once we'll get e iota omega t, and then once we'll get this minus iota omega t. Okay, we'll get this. Yeah, is this okay? Now what we'll do, we know this e to the power iota theta plus e to the power minus iota theta, we can write that as 2 times cos theta. Okay, so let's take this 1 over 25 outside, and then this becomes 9 psi naught squared plus 16 psi 1 squared, and this will become, because we will have additional 2, so this will become 24 psi naught psi 1 cos omega t. Okay, so this is what we have, 1 over 25 outside, this is mod psi x comma t squared. Yeah, finally. Now if you remember, we had a similar expression in the problem. Yeah, here. So we have a coefficient of psi naught, coefficient of psi 1, coefficient of psi naught psi 1, and a 1 factor outside. So if we compare what we get, if we compare with this equation, we clearly see that we have this 1 over 25 thing outside, then 9, then 16, and then 24. So 25, 9, 16, and 24. Okay. Is this clear? Yeah?
Yes.
Okay, good. Okay, then let's go to a two-state system. So these two-state systems are very, what do you say? Like you'll encounter them very frequently in when we study quantum mechanics. So basically we only have two states, state 1 and state 2. Okay? And we have a Hamiltonian which is written in terms of these states. So what is our Hamiltonian? H is written in terms of these states. We have some number A, then we have 2, 1, 1, minus 3, 1, 2, and then minus 2, 1. Okay. So there is 1, 1, 1, 2, 2, 1, but there is no 2, 2. Yeah, there is no 2, 2 state in the Hamiltonian. And there is some A, okay, they have mentioned that A is a number with dimensions of energy. What we have to do, we have to find the corresponding eigenvalues and eigenvectors. Okay, so how do we do that? So anyone? So how to start? What should be our first step of solving such problem? Okay, so the first step should be that we write this Hamiltonian H as a matrix. Yeah, So here for example we can write H as A and then this matrix 2, because this is 1 1, and this 1 2 is minus 3, so minus 3, and this 2 1 is minus 1, so minus 1, and this 2 2 is 0, so 0. Okay, so let's solve for the characteristic equation. What is the characteristic equation? That the determinant of h minus lambda I, and that is 0. So what will that give? That will give us the eigenvalues lambda. Yeah. So this becomes 2a minus lambda, this becomes minus 3a, this becomes minus a, and this becomes minus lambda, and this is the determinant is 0. Okay, so this becomes 2a minus lambda and then minus 3a squared, so this is 0. Okay, so finally we get this equation lambda squared minus 2a lambda minus 3a squared is 0. Now this is a quadratic equation, and I think we can, yeah, we can factor it as lambda minus 3a and lambda plus a is equals to 0. Okay, so what are the eigenvalues that we are getting? So lambda 1 is 3a and lambda 2 is minus a, so 3a and minus a. So already option D. But let's also find out the eigenvectors, and then we'll check if the eigenvectors that we are finding, they are consistent with the answer that we have selected. Okay, so first let's find out for lambda 1 is equals to 3a, this one. So lambda 1 is equals to 3a. So how do we find the eigenvectors? So basically we write our Hamiltonian, which was this thing, right? And then here let's take this eigenvector, and we know that the eigenvalue is 3a and we should get the same eigenvector. Yeah. Right, so this is basically h psi is equals to e psi, or here in this case the eigenvalue is lambda, so lambda psi. Okay, so what will this give us? So this will give us 2ac1 minus 3ac2 is equals to 3ac1. So essentially we'll have minus ac1 is equals to 3ac2, and second equation, and this will give us, this will give us c1 is equals to minus 3c2. Okay, so if our c1 is 1, so then our if our c2 is 1, then our c1 will be minus 9. So basically we can write the wave function as minus 3 1 plus 2. Okay, and then if you want to normalize, so we'll get 1 over root 10. Yeah, so notice that this c1 here, this is minus 3 times c2, which we have just taken as to be 1. and this 3 squared will give us 9, 1 squared will give us 1, so the sum is 10, therefore we have normalized by 1 over root 10. Okay. So for lambda 2 as minus a, what will we have? We'll have the same thing. C1, C2, and here instead of 3a we'll have minus a C1, C2. So this thing will give us minus a C1, and this is already minus a C2. So this will give us minus a C1 is equals to minus a C2. So this will give us C1 is equals to C2. So basically 1 1 matrix, and the eigenvector will be 1 by root 2, and then this 1 plus 2. Okay, so let's check if we are getting same as them. Yeah, right. Any doubts in this?
Okay.
Yeah, okay. So let's move on. So what we have here, we have a particle in state P, which is written in terms of states 1, 2 and 3, which form an orthonormal basis. Okay, so we are given 1, 2 and 3 form an orthonormal basis. Then we are also given some observable B, which is again written in terms of 1 and 3. And then the question asks, what will be the probability of measuring B in such a state? Okay, so notice that we have a state P, which I think is normalized, yeah, which is normalized. So this will give us 9, this will give us 4, so 13, and then 7. So this is normalized. Yeah, so our particle is in this state, and then we have some observable B, which is written like this. Right, and then the question asks, what is the probability of measuring small b in such a state? So the what we notice that the eigenvalue small b of the operator b, this small b, this corresponds to the third state, say this state 3, right? And then what is the probability that our particle is in state 3? We can simply write that as, so probability that our particle will be in state B will be just mod C3 squared, yeah, mod C3 squared, where C3 is the coefficient of this third state. So under root 7 by 20, under root 7 by under root 20, and then mod squared, so 7 by 20. So option D. Okay.
One thing, since there are three orthonormal bases.
Sorry.
There are three orthonormal bases given, 1, 2, and 3.
Yes.
So can we write it in matrix form? Because matrix would require an even number. If square matrix, then maybe 4 we need. Or shall we say that P, the particle is in a state where P4, the basis 4 is 0, the probability of basis 4 is 0. I mean,
Why?
that makes
Okay, no, just okay. Sorry. Why do you say that we cannot write this in a matrix form?
Because matrix would require, see, if I say the observable capital B, then it has the diagonal terms A and B, 1, 1 and 3, 3. Maybe that corresponds to the diagonal term.
Yes,
Uh,
you are
So,
you are correct.
so that
So
means we should have
because
some
yeah.
orthonormal basis 4
Mm-hmm.
also to
Mm,
complete the matrix. Or
no,
I'm
so
missing something.
no. I think you are missing something. Let's say, for like in the previous problem, we had just two states, right? One and two. So when we have two states, we require a two by two matrix
Okay, okay.
to describe the Hamiltonian.
So
Here,
this is
because we have
matrix.
three states,
Okay,
we will require 3 by 3 matrix. That's
okay.
it. So if you
So
want to
here,
write this B, so
hmm,
it's diagonal. So okay, let's write it out. It's very simple. So this will be A and this will be B. Remaining everything is 0. 0, 0, 0, 0, 0, 0, 0. Yeah, this is B.
yes, yes, yes. Okay, got it.
Got it? Okay.
Yeah.
We don't need a fourth state with zero probability.
No,
That is
right,
just
exactly.
redundant. Yeah. So
Hmm.
we can add these zeros, right? If you want fourth state, but that is just redundant, not required.
Hmm.
That will not change anything. If you want, you
Okay.
can add, but that's not required.
Hmm.
If you have, okay, so if you have, what we basically then what we can conclude, if we have n state problem, we can write it in terms of n cross n matrix. Okay,
Hmm.
so
Hmm.
our operators, these things will be uh, n cross n matrix, whereas our states will be n cross 1 matrix, right? N cross 1.
Hmm.
So just like vectors, we can also write this p as a vector here. Yeah, we can write this
Hmm.
as a vector here, corresponding to 1, 2 and 3. So this will be, for example, 3 by root 20 and so on.
Hmm. Hmm.
Okay, okay,
Yeah.
okay. So let us then move on. Again, we have sorry, we have three orthonormal bases, so three levels, 1, 2 and 3, and we have an operator A, which is written in terms of 1, 2 and 3, again a perfectly diagonal matrix. And the question asks what will be the possible measurable values of observable A. So we just solved one problem right now above, and this is also a very straightforward problem because we have just solved one above. Okay, so let's write down A. So A is 7, 1, 1, yeah, plus 9, 2, 2, sorry, minus 5, 3, 3. And then we are asked about the measurable values of A. So the measurable values of observable A. Now when we want to measure any value of any observable, so what happens? Our our wave function collapses to one of the states, right? So either it will collapse to state 1, state 2 or state 3. If it collapses to state 1, right, so what we will have, so our operator, if it acts on state 1, so these last two terms will just give 0, and what will be left with is this first term and then this. So essentially, because this is orthonormal, so this is giving us 1, right? So we can just remove this thing and we are left with this. So what is the value that we are getting? We are getting 7, right? Similarly, for state 2 we'll get 9, and for state 3 we will get -5. Okay, 9 and -5. So option B.
Do we really need to worry about the normalization here of A?
Yeah, so A is actually not a wave function. Yeah, it is an operator, right? If it were some wave function, then yeah, of course, we need to worry about the normalization. The normalization that we need to worry about was this thing, right? When we had this quantity here,
Mhm.
yeah, but it is given that this is orthonormal basis. That's why we can simply write this as 1.
So
If,
what is the dimension of this 7, 9 and -5?
sorry,
What are the dimensions? What could be the possible dimensions of the
mm-hmm.
possible measurable values of the observable E?
Dimensions, okay. So whatever is the dimension of this operator A will be the dimension of 7, 9 and 5. For example, if this is energy, then the dimensions will be energy. If this is momentum, this will be momentum. So the dimension
Okay.
that A has will be the dimensions of these 7, 9 and -5. We don't know, there is no mention what this operator is giving us. Okay, we don't know. Maybe this is a number operator which is telling how many particles are there in each state. Okay, let's say this is a number operator, then they won't have any dimensions.
Okay.
Yeah, so then
Yeah.
it is measuring, okay, so there is there is some 7 particles in state 1. Okay, but okay, it also has one negative number, so it won't be a
Number.
number operator, but
Fine.
let's say a momentum operator. Yeah, it can definitely be a momentum operator.
Got
Okay. Okay, so that's it for today, I guess. But we can solve a few more. Okay. Okay. Let me write down one problem. Okay. So let's have an operator d by dx. Find eigenvalues and eigenfunctions. Okay. So this is the problem. So how should we proceed in this case?
Can we apply Schrodinger equation in this to find that?
Uh, Schrodinger equation is for a very specific operator, which is Hamiltonian.
Right, because this is actually momentum. Now, yeah, this is momentum. H cross is
Yeah.
missing in this.
Yes. And also for
Its
Schrodinger equation,
imaginary
we
part is
have,
missing. Rest is there.
yeah. Also, because the Schrodinger equation has momentum squared, so we have
Yeah,
d2
yeah,
over
yeah. It
dx
can't,
squared.
so you cannot apply that, right?
Yeah. So what do you think we should do?
Maybe we can apply it on some function. We can
Yes,
consider a function and
we
then
can
apply
consider
it.
a function. Let's operate. Okay, so let's consider some random function f of x. Yeah, and then when we operate this operator on f of x, if we get some lambda times f of x back, then we say that this lambda is an eigenvalue of O, and fx are the corresponding eigenfunctions. Okay, so we'll make use of this equation.
Ex is can be one solution in this because Ex will remain Ex,
Yes,
right? And with
exactly.
the one as a eigenvalue, right?
Exactly, exactly.
Yes,
So
sir. Maybe some iota, exponential iota will also be
basically any exponential
any
function,
exponential,
right?
any
And it
exponentially
will just,
decaying or increasing or any.
yes, exactly. So you are already getting the hang of it. So okay, so let's operate d by dx. So what we'll get? We'll get d by dx f of x is lambda times f of x. Okay, and then what we can do? We can write this as d fx over fx is equals to lambda times dx. Okay, something that we used to do in differential equations. Yeah, when we
This will
solve.
give log of this, huh?
Correct. So now what will be natural step? Integrating both sides. Yes. So upon integrating, what we'll get? So we'll get log of this function f of x. Yeah, log of this entire thing, and then here lambda x plus c. Okay, so our function will be e to the lambda x plus c. Yeah, or we can take this e to the c as some constant. We can write it as a. Okay, where a is e to the c. Okay, so this is the eigenfunction, and any exponential function that we take will be an eigenfunction of this operator, and the coefficient of x in that exponential function will be our eigenvalues, right? As you said, for example, we can have lambda is equals to 1 iota, 2 iota, 100 iota, 100, minus 100, anything. Okay, is this clear?
Yeah, any complex number. Any
Yeah, any basically any complex number. So lambda is any complex number. Okay. Hmm. We will just ensure that this function does not, like, if this, if we want to have it as a wave function of a real particle, then we will make sure that it does not violate the quantum mechanics postulate. So this function basically should not diverge to infinity at some point. Yeah, so we cannot have, when x tends to infinity, so this function fx uh, should go to 0. So basically this mod of fx from minus infinity to infinity should be 1, right? So that the probability of finding the particle from minus infinity to plus infinity is 1 and it is not diverging. Okay, but there is no mention of a real particle or anything. It's more like a mathematical problem, not a physics problem, that we have this operator, just find the eigenvalues and eigenoperators. Okay, any doubts in this? No? Okay, similarly, what you can try, or what you can like even think of, what would happen if we take the double derivative? Okay, and now as we had our discussion just few moments back, then that double derivative d2 by dx squared, yeah, so that will, okay, so the squaring this thing, so that will just give us the,
Sine cos can work there. Sine cos.
exactly, so that will be like a free particle that we study. Okay, so that we already know what we will get, right? That is basically the free particle Hamiltonian. Yeah, just divided by the mass of this particle. That's why we get a sine function for a free particle.
I think there we need to take care that there should be a negative sign. Then we will get the
Yes.
sine and cos. Else we might get shine and cos. Have you got it?
Yeah, basically, what we do there is we write p squared, and because this p has this iota there, and then if we square that thing, so this iota squared becomes -1. Yeah, that's it. So minus h cut square over 2l. Okay.
Yeah.
Yeah. So that basically gives us sinusoidal functions. The second one. The first one is giving us exponential functions. Second one will give us sinusoidal functions, and we know that corresponds to the Hamiltonian of a free particle. Okay. Should we do one more, or is that enough for a day?
Yeah, maybe one more. We have 10 minutes.
Okay. So let me find one similar one. Okay. Okay, let's solve this. So we have an operator A, which is a function of time. Okay, so this contains time as a parameter, and now we have to use the time dependent Schrodinger equation for the Hamiltonian H and the Hermitian property of H, and we have to show that the expectation value of A, if we differentiate it with respect to time, it goes as this thing. So for A, some operator A, which has time as a parameter, show that, so we'll have its expectation value, right? How this expectation value changes with time is given by this equation. Okay, this is like, for example, if this A is x, the position operator, so this will tell us how the expectation value of position is changing with time. Okay. Okay, so how do you think we should begin for this problem?
Is it somehow related to Ehrenfest equation? I don't know.
Yeah, does it look kind of similar to the
It looks like,
Ehrenfest equation?
although I don't know anything about that, but I just saw it somewhere, so that's why.
Yeah, it is actually. That's why I chose this, because our that thing we could not cover earlier. So with the help of this problem, we'll have some idea about the Ehrenfest theorem.
This last term is this bracket or what?
Sorry,
Del
so
del.
this is, yeah, sorry, my mistake. This is the expectation value. This thing.
Okay.
Hmm. Okay, so first of all, we should notice that everywhere on the right hand side we have the expectation values, right? So let's write our expectation values. A, this will be some psi, and then operator A, and then psi. So this is how we define the expectation values. Now we differentiate it with respect to time. Okay, so basically what we will have dA over dt. So we have to apply product rule here. So how do we apply a product rule in such problems? Do you know that we have to take the partial derivatives?
Is it del psi by del t, then the other two constants, then del a by del t,
Correct,
type
correct.
space constant, then
Yes.
the half term.
So we'll have three terms basically. So this will be del psi by del t, other two terms, yeah, a psi, and then psi del a by del t, psi, and then this psi a, and then the last term. So del, sorry, del psi by del t. Okay, just the product rule. Now we have to use the time dependent Schrodinger's equation. So what is the time dependent Schrodinger equation? We know the time dependent Schrodinger equation is nothing but this thing. Correct? So h psi is this thing. Okay. Solving this only gives us that uh, exponential phase that we multiply when we want to write a time evolution. Okay, so this is the time dependent Schrodinger equation. When we solve this, only then we get the basically the, so basically what we do, we write this as E psi, and then if you just solve this equation, you can already see that what we'll get some Et by h cut, some exponential Et by h cut thing, right? Okay. So this is not required here, only this thing is required. Okay, so from here we notice that we can write this del psi del t in terms of the Hamiltonian h. Okay, so our del psi over del t, we can take this here and multiply this side. Okay, so let me shift this here, and this becomes minus iota over h cut. Okay, okay. Now similarly we can write the, so this is the ket form, we can also write the bra form. So what will be the bra form? So the bra form will be del of psi over del t, and this will become plus iota by h cut psi and then h dagger. Correct? So I have just taken the adjoint of the above equation. Is that okay? So iota becomes minus iota and this order changes. Now we know that our Hamiltonian is a Hermitian operator. So I can get rid of this dagger and I can just leave it like this. Is this okay? Yeah. So already we can see that somewhat we are getting close to the right hand side. Okay. So essentially what we can do, we can just substitute both these things back in the equation. So we will get dA by dt. So this just becomes iota by h cut h, right, and then this a psi, right, plus this thing remains as it is, del a over del t psi, and this last term, this becomes psi a, and then here we will have minus iota by h cut and h psi. Okay, so now we can group the first and the last term and take out this iota by h cut outside. So we'll have iota by h cut. So this will become psi. So this is h a psi, and here we'll have minus a h psi. So h a minus a h, and then psi. And what is this term? This term we can simply write as expectation value of del a by del t. Yes, that's the definition of expectation value. So this is what we have. And now what is this HA minus AH? We can write HA minus AH in terms of the commutator. So this becomes iota by h cut, and then so this is psi and this is psi. Again, basically the expectation value of this commutator h comma a plus del a by del t. Okay, this is what we wanted to prove. So this is our Ehrenfest theorem. Yes.
On the left hand side, we have complete derivative, but on the right hand side, on the last equation,
Yes.
but on the right side, it is the partial derivative of a. When we take the expectation value of del a by del t, it is a partial derivative.
Yes.
So why is this discrepancy?
Okay, so I mean it is just coming out mathematically, but one thing is to think about is like what will happen when your Hamiltonian commutes with your operator a, for example. Then this h comma a will be 0, right? So this first term basically vanishes. So then
This means that A is purely function of t
correct,
and
correct.
it's independent of x.
Yes, exactly.
So the full derivative is equal to the partial derivative, right?
And yes, exactly. You are absolutely correct.
Which is why it is commuting with h, because h is basically p square by 2m, right?
Yes, yes,
That means if a is p square, if a is p square,
yes. Which is basically your kinetic energy. Yeah.
yeah,
So if A is your kinetic energy, then your
then
kinetic energy is independent of your position. Yeah.
and any other example otherwise?
Uh, so basically, okay. So this is generalized form of Ehrenfest theorem that you asked about in the beginning.
Yeah.
Okay. Why this theorem is important? Because it serves as a bridge between quantum mechanics and classical mechanics. So in classical Hamiltonian mechanics, we have this equation. So dA over dt. There we don't have any operators. There we have Poisson brackets. Okay, this comes when you study Lagrangian and Hamiltonian in classical mechanics. Sorry, this will be plus and del A by del T. This is completely classical equation. Okay, where A is any observable quantity. It may be energy, momentum, whatever, any observable quantity. And this is classically, this is true. Okay, now if you compare this quantum mechanics equation Qm and the classical equation, you can already start to see some similarities in the form, right? So this Poisson bracket is very similar to this commutator.
Yes, yesterday or 2 days ago, I read about this Poisson bracket,
Yes, yes.
but I don't know what it is. What does it mean? What does this A H in this Poisson bracket mean? Like in quantum, when I
Yeah.
say commutation of H and A, then that is HA minus AH.
Mm-hmm.
What about this Poisson A comma H?
Okay.
What that mean?
So one thing. Okay. So firstly, what we should keep in mind that here these are operators. Okay, I should put these as operators.
Yeah.
But here these are not operators. So for example, here H is just your total energy of the system. It will not operate on anything. These are observables. Okay, so this,
Okay.
let me write, these are observables. Okay, so you can think it in terms of some numbers. Okay, so this H will be like, let's say 20 joules or something. But here these are like matrices.
Okay.
Okay, these are like matrices. So Poisson bracket is, okay, let's say if you have two quantities, let's say F and G, and you want to find out the Poisson bracket of F and G, and okay, first of all, they'll be uh, they'll be functions of, let's say, P and Q, where your Q is the position coordinate and P is the momentum coordinate. Similarly, your G is also P and Q. Like in the beginning, we took the Lagrangian, right, which is
Mhm.
x
Yeah.
and x dot. Similarly, here we have P and Q.
Okay.
So then this F and F comma G, then it is defined as del F del Qi del G del Pi minus del F del Pi del G del Qi. And if you only have just one direction, let's say only x direction, so this will be del F over del x, del G over del Vx, which is the x velocity, and similarly del F over del Vx, del G over del x. Okay, something similar to the commutator, right? Something similar in
And what is the
terms.
significance?
Sorry.
What is the significance of this? What are we trying to calculate by this summation?
So this basically, if you find out this Poisson bracket, then this will give you how this quantity A evolves in time.
Like for that, you give an example of pendulum, no? Maybe next time, if you can give an example of this. That was very beautiful example. The
Sure,
pendulum was
sure.
very beautiful.
I can continue that pendulum example in the next class using this Poisson bracket.
Using Poisson bracket.
Yeah, we'll see how let's say how the kinetic energy changes with time. So the time
Using this,
derivative of the kinetic energy for a simple pendulum.
okay, using this thing, Poisson
Yeah,
bracket.
yeah, I'll try. Or else I'll give some other example, but I'll see this
Yeah, yeah,
Poisson
that would
bracket.
be great. That would
Okay.
be great.
Okay. So we'll do that next class.
Yeah,
I think
thank you.
it's time. So let's call it a day.
Yeah, thanks a lot.
Yeah, you're welcome. Okay.
Thank you so much.
You're welcome, ma'am. So see you next Saturday then. Have a
Yeah,
good evening. Bye bye.
good evening. Bye.